polybasic acids. Look here. Previously, we have seen the titration curves of monobasic acid. Whether it is a strong acid or a weak acid, that is not the problem. The strong acid had only one basicity, and the strong base, therefore, only one neutralization point. And that equivalence point, where actually the pKa value and the buffer concentrations become equal, therefore it almost reaches the pKa value. pH is equal to pKa. Similarly, in the case of weak acids also, the equivalence point is there. This is regarding the weak base and the strong acid. Now we are going to see another different thing called polybasic acids. Acids containing more than one replaceable hydrogen atoms, more than one replaceable protons at various different points. You should carefully look at the diagram. Look at the diagram. Phosphoric acid has 3 pKa values. First of all, you look at this equation. H3PO4 aqueous. When it combines with OH minus, only one proton is replaced. One proton comes out, becomes water, and the anion that you are getting here is a H2PO4 minus. So the formation of H2PO4 minus from H3PO3, this equilibrium exists at the pKa 2.16. So this is one proton replacement. So the titration proceeds like this. So this is the first equivalence point, where the pH is equal to pKa1, the first dissociation constant, pKa1, which is equal to 2.16. When the titration proceeds, you see, I am going on adding sodium hydroxide. When I am going on adding sodium hydroxide, again the pH increases. It goes. And then what happens? This is the first equivalence point. This is the half equivalence point, where the pH is equal to pKa. And there is a second equivalence point here. And in between, there is a flat zone. As we have discussed earlier, there is a flat zone. This is called a half equivalence point, where the H2PO4 minus loses one more proton and becomes a HPO4 minus. Watch closely. At this point, for the first pKa1, phosphoric acid loses only one proton. And the ion formed is H2PO4 minus. And at the second level, at a different pH, at a different pKa value, say 7.21, phosphoric acid loses one more proton and it becomes a HPO4 minus. Whereas the reactant side, it is a H2PO4 minus. It becomes a 2 minus after losing one more proton. Again, the titration proceeds. It goes on and it meets the second equivalence point, the vertical line. Whereas this is the buffering line, buffering zone. This buffering is observed at pH 7.21, whereas the first buffering is observed at a pH 2.16. So it goes on, and then one more proton is lost. That HPO4 minus, it loses one more proton and becomes a PO4 minus, and there is no further more titration because the acid unit now is not having any H plus ions. All the H plus ions are lost. So the third half equivalence point, which is the buffering zone, appears at a pH of 12.32. And then there comes a third equivalence point. So this is how the titration of a polybasic acid proceeds. So the polybasic acid means you should understand basicity of an acid is the number of replaceable hydrogen ions present in the acid. Acidity of a base is the number of replaceable OH groups present in an acid. So the phosphoric acid has three pKa values. At three different pKa pH levels, three replaceable hydrogen atoms are removed one after the other. In the first pKa 1 value, that is 2.16, phosphoric acid loses one proton and the equilibrium exists between H3PO4 and H2PO4 minus. And in the second level, at the pKa 7.21, it loses one more proton. So the equilibrium is between H2PO4 minus and HPO4 2 minus. At the third level, the equilibrium is between HPO4 2 minus and PO4 3 minus. Therefore, it has three pKa values. And another important aspect or interesting aspect about the polybasic acid is the pKa values are wide separated. Look here, it is 2.16, it is 7.21, it is 12.32. So the values are wide separated. As the values are wide separated, this will experience the buffering in three different regions. In three different regions, you can experience the buffering. Similarly, another polybasic acid is citric acid. And citric acid also shows pKa values. Actually, that graph I'm not having at present. I will be showing you at a later stage. But it shows the buffering at, again, three different regions. But in this case, the buffering, the pKa values are very close. Say 3.1, 4.7, 6.4, 3.1, 4.7, 6.4. Therefore, relatively flat throughout. And also the pKa values are very close. Therefore, the citric acid buffers can be used in a long range of pH. So that is about the citric acid. So the polybasic acids, we have seen citric acid and the phosphoric acid. Now, pH and ionization of amino acids. This is another important aspect you should understand before going into the biological applications of the buffers. Look here, what is an amino acid? So, amino acid is a system containing both amino group and acid group. Acid group is ionizable. Amine group is also ionizable. Here, this is the ion where both acid and amino group are ionized. See, NH3 plus is there, COO minus is there. Normal amino acid will be like this: R, C connected to R, H, COOH, NH2. That is normal unionized amino acid. If only amino group is ionized, then it is a cation, because the entire ion is possessing only positive charge. If the carboxylic group alone is ionized, it is called anion, because NH2 remains unionized. It is called anion. But if there is a condition where both amino group and acid group are ionized, this is neither cation nor anion, but it is called Zwitter ion. That is, both the carboxylic group and the amino group are ionized. See, for this dissociation, there is a pKa value. Let me say this is pKa 1. For this conversion, there is another pKa value called pKa 2. But the pH of the Zwitter ion is equal to pKa1 plus pKa2 divided by 2. So this is actually, this H doesn't have any significance. This is pH is equal to pKa1 plus pKa2 divided by 2. So this is the pH of this Zwitter ion. Now we are going to see the biological importance of buffer. All the proteins are made up of amino acids. You know, amino acids are interconnected. They are interconnected by a special bond called peptide linkage. Because that is C double bond OH plus NH2 after the elimination of a molecule of water, what is formed is the amide group, and this is called a peptide linkage. So a long chain containing amino acids in a particular sequence, they form the protein. When proteins are hydrolyzed, you are getting amino acids. So protein at one end, it will have a carboxylic group. At the other end, it will have amino group. In between, it will have a number of peptide bonds. So as a whole unit of protein, it can act as a buffer. But the ionization of either the carboxylic group or the amino group are observed only at the terminals. The in-between interlocked or intact amino acids cannot be ionized unless the protein is dissociated. So every protein has an isoelectric point. Isoelectric point means the pH at which the Zwitter ion is formed. So the protein, I want to tell you a few more extra information. The protein denaturation or the ionization of amino acid is a pH dependent. Probably you will be having silk sarees at home. Actually, the silk saree is containing silk thread, where the silk thread is secreted by the silkworm. Actually, the silkworm is constructing a cocoon to survive around it using the secretion of its own mouth, which is a protein. That protein is called a silk fibroin. This silk fibroin has the structure of pleated sheet-like structure. The pleated sheet-like structure is stabilized by the hydrogen bonding formed between COOH and NH2 groups. That is why silk sarees are not washed as we wash the cotton things, because the proteins and the amino acids will get disintegrated when the pH changes. Similarly, alpha helical proteins. We know the egg albumin is a protein. Even our hair is a protein. That is why we are not using soap for the hair. We use a conditioner for the hair, because conditioner is the substance whose pH is adjusted to wash proteins. So amino acids inside the protein chain are non-ionizable. As the terminal amino acids are ionizable at various pH levels, the three-dimensional structure of a protein is also pH dependent. That is what I said. When the pH changes, the pleated sheet, like beta pleated sheet structure, will get collapsed. Even the alpha helical system will get collapsed. So the proteins, they lose their structure, they lose their nature, which is called the denaturation, which will take place when the pH is altered. So the biological systems which is containing the protein, will maintain the pH at various places by metabolic production of lactic acid and ammonia. See, the lactic acid production and the ammonia production, they are all just to maintain the pH. Suppose a man is drinking too much of alcohol. Our biological system is designed to function in the presence of water molecules, not in the presence of alcohol molecules. So when the alcohol is taken, what will happen? It will try to readjust the system and bring it back to the original condition. So the rearrangement involves maintaining of the pH at various places. This maintenance of the pH will be by the production of ammonia in the liver. So what happens? The quantity of the ammonia in the liver increases, and automatically heat of bodies will increase. So this is pH adjustment. Suppose if you work hard, you are exhausting yourself, then more amount of a carbon dioxide is given out and more amount of oxygen is taken in. That itself will affect the pH of the blood. There will be variation of the pH in our body because we gasp, our respiration rate will increase, heart rate will increase. Even in such situations, the pH is maintained by the production of lactic acid. So why during night when you are given milk, you feel sleepy? Because of the lactic acid you are taking. Similarly, when you are working hard, you are feeling tired and sleepy because of the lactic acid production in our body itself. So taking milk directly gives lactic acid to the body. But when you are physically working, it produces lactic acid in your body. These are all because of this ammonia, but actually the alcoholic, that smoothness in the mind or sedation in the mind is because of the ammonia synthesis. So whatever you do in your body to change the pH of certain systems, the system will try to bring the pH to the normal level by the metabolic production of lactic acid and ammonia. Even protein metabolism is also plays an important role in the pH maintenance of our biological systems. So the blood pH is maintained mainly by bicarbonate buffering, phosphate buffering, and also proteinate buffering. So different types of buffering are taking place in our body to maintain the pH of the blood, to maintain the pH of every acid as such. Because when the glucose is burnt in the mitochondria, even there involves a pH alteration. That is why the blood which is running in the arteries and the blood which are running in our veins, they have different pH values. Because arterial blood is oxygenated blood, except the pulmonary artery. In our body, arteries are the blood vessels carrying the blood from the heart to the various parts of the body, which is taking oxygenated blood. Veins are blood vessels which are carrying the deoxygenated blood from various parts of the body to the heart. But if you closely look at the blood vessels connecting the heart and the lungs, the deoxygenated blood has to be carried from the heart to the lungs to get oxygenated. At the same time, the oxygenated blood has to be taken from the lungs to the heart to get the oxygenated blood. Therefore, in pulmonary arteries, deoxygenated blood is flowing. In the venous pulmonary veins, oxygenated bloods are flowing. In all other parts, arterial blood contains oxygenated blood. and the venous blood contains deoxygenated blood. Therefore, the pH is also different because the blood containing more amount of oxygen will have a different pH. And the blood containing more amount of carbon dioxide will also have a different pH. That is why the arterial blood and the venous blood have variation in the blood pH, but the variation is not much pronounced. See, arterial blood pH is 7.38 to 7.42, whereas the venous blood is 7.36 to 7.40. There is not much difference. If at all the pH variation goes below 7 or above 7.8, the effect will be lethal, fatal effect. So the pH biological importance is of much concern. So the biological importance of a buffer is this. Now these are all my 2 channels. You can visit and you can go through all the video lectures. I think you do not have any doubt.